Let's start by picturing the area under a curve, cut into thin vertical strips. Each strip is a rectangle of width delta x, and its height is the function value at some sample point inside that strip. If we add up all these rectangle areas, f of sample times delta x over and over, we get an approximation to the area under the curve. This sum is called a Riemann sum. Now, the definite integral from a to b of f of x dx is defined as the limit, as n goes to infinity, of that Riemann sum. In other words, we let the number of rectangles grow without bound, and the width of each one shrink to 0, so the approximation becomes exact. Next, the fundamental theorem of calculus, part 1. If we define f of x to be the integral from a to x of f of t dt, then the derivative of f of x, that is, f prime of x, equals f of x. So integrating and then differentiating just gives you back the original function. Now, part 2 of the fundamental theorem of calculus. If f is any antiderivative of f, then the integral from a to b of f of x dx equals f of b minus f of a. This is what lets us evaluate definite integrals quickly, just using antiderivatives without ever computing a limit of sums directly. Let's now work through an example. We want to evaluate the integral from 1 to 3 of the quantity 2x plus 1 dx using part 2 of the fundamental theorem. First, we find an antiderivative of 2x plus 1. That antiderivative is f of x equals x squared plus x. Now we evaluate this antiderivative at the upper limit, which is 3. F of 3 equals 3 squared plus 3. That is 9 plus 3, which equals 12. Next, we evaluate the antiderivative at the lower limit, which is 1. F of 1 equals 1 squared plus 1, that is 1 plus 1, which equals 2. Finally, we subtract top minus bottom, so 12 minus 2, which equals 10. So the integral from 1 to 3 of the quantity 2x plus 1 dx equals 10. Here's an important trick to remember. Whenever you write an indefinite integral, one with no bounds on it, you must always add plus c, the constant of integration. But on a definite integral, never write plus c, because when you subtract f of a from f of b, the c's are identical and cancel out automatically. Now, a common trip-up. Learners very often reverse the order of subtraction, computing the antiderivative at the lower bound minus the antiderivative at the upper bound, instead of the other way around. This mistake happens especially often when the lower bound happens to look like the bigger number, which can trick your instincts. Watch out for that sign error. It flips your final answer, negative. So here's a teaching tip to help you avoid that mistake. Say this fixed phrase to yourself every single time. Top minus bottom. And by top and bottom, I mean the upper limit and lower limit exactly as they are physically written on the integral sign. The number sitting on top minus the number sitting on the bottom, not whatever order the numbers happen to appear in a sentence.